assignment? I'll do some of those problems for you. That'll be pretty spiffy, huh? Actually, you know what? Did anybody print out the newest homework? The one that I just posted. I posted last night. It's like homework 13 or something. I can make up problems.
That's the one that has an extra credit opportunity on the back.
That might be. Do you have that one? No, that's okay. That's all right. I can make up problems. All right, this is limiting reagent. We're talking about limiting reagent today. And limiting reagent has to do with what runs out first, the stuff that runs out first. And you're doing these limiting reagent problems, you can think them through, or you can follow a particular set of steps. Here are the steps that I'm going to advise that you follow. You can do whatever you want, but these are the ones that I recommend. Step number 1, convert all quantities into moles. So you already know how to do that. You learned that a week ago. Mass to moles or number of particles to moles. So you start out with moles of whatever you got. Step 2, divide moles by the coefficients in the balanced equation. Step 3, smallest number from number 2 above is the limiting reagent. So LRs, we're going to call it our limiting reagent. And then step 4, start all stoichiometric calculations with the limiting reagent. So you already know how to do stoichiometry between using the whole stoichiometry flowchart. You're going to now employ that in a little bit different context with this idea of limiting reagent. We'll look at our stoichiometry flowchart again. Remember, you know you can go from grams or number of particles into moles of that first substance. And what gets you here is the molar mass. And this is Avogadro's number. Moles of A to moles of B. This number is our mole-bridge ratio. Comes from the balanced equation. And then we go from moles of the second substance to grams or number of particles, and we can use our same conversion factors to get there, either molar mass or Avogadro's number. All right, so with that as the backdrop, let's start a problem. Let's say, okay, how about nitrogen gas and hydrogen gas makes ammonia gas. This is actually called the Haber process. That was made popular in World War II. They had to make lots of bombs, and bombs need lots of ammonia, so they had to make lots of ammonia. Now to balance this is a little tricky. How would you balance this thing? What coefficients would be necessary? I think we need a 2 there, right, to fix the nitrogen, and then a 3 for the hydrogen. All right, I like this one because we've got a 1 to 3, a 1 to 2, or a 3 to 2 ratio that's going to be helpful when we're doing these kind of problems. So say, for example, I started out with the problem would say you have, 1.7 grams of nitrogen gas. Say we got a whole bunch of hydrogen gas. Say we have 40.3 grams of the hydrogen gas. We want to know how much in grams of ammonia can I make. So we got to use our limiting reagent idea. So the very first step, we go through our steps here, is we're going to convert all quantities to moles. So I'm going to start with the 1.7 grams of N2, and I'm going to go from grams of N2 to moles of N2. 1 goes in front of N2, but how many grams is a mole of N2 going to weigh? 28. Excellent. Make sure you know that it's not 14. Second one, I'm going to take 40.3 grams of the H2, and I'm going to go from grams of H2 to moles of H2. 1 goes in front of moles, and we know that it weighs 2.0 grams. All right, somebody with a calculator, do that top one for me. This one's going to be that one in my head. What's this one with somebody with a calculator? What's 1.7 divided by 28? 0.06? So even though we had a huge whopping amount of hydrogen in comparison to nitrogen, the mole ratio isn't all that, that much of a difference. So which one is our smaller number of moles? N2 is the small, oh, wait, we have to divide by the coefficients. Whoopsie, I'm not following my steps here. Step 2, we're going to divide the number of moles by the coefficients in the balanced equation. Now we got to use the coefficients, which in N2's case, what's the coefficient here? 1, because there is no coefficient, so we assume it's 1. What's the coefficient for H2? 3. All right, so 0.06 divided by 1 is still 0.06 for the N2. What's 20.5 or 20.15 divided by 3? 6.72 is for the H2. All right, so what's the smaller number? All right, so there's our limiting reagent. So now we have to start all of our calculations with the limiting reagent. So now we're going to go back to the original information in the problem, and I always put a little symbol to myself that that's the limiting reagent. Okay? So I'm going to start with that, 1.7 grams of N2. And now, using my stoichiometry flowchart, where am I going to go? From grams of N2 to moles of what? N2, right? So I went from grams to moles. Now I need another conversion factor to get me from moles of N2 to, what's my next step? Moles of the stuff I'm making, in this case the ammonia. And the last step, I'm going to go from moles of ammonia to grams of ammonia. All right. Moles of N2, we know weighs, what did it say, 28 grams per mole. Where do I get the coefficients here? Balanced equation. So NH3's coefficient is 2. N2's coefficient is 1. And a mole of NH3, I think that's 14, that's 17 grams per mole. All right, somebody with a calculator. What's 1.7 divided by 28, enter, times 2, enter, times 17, and what are my units here? Grams of NH3. All right, let's think about sig figs. Remember, the initial information in the problem is what I'm going to base my sig figs on. How many sig figs are there? 2. So what should I round that to? 2.1 grams of NH3. All right, now what if I asked you what mass of excess reagent remains? That might be a question on your homework or on the exam. Let's think about that. What would I have to figure out in order to figure out what my mass of, first of all, what is the excess reagent? Which one?
H2.
All right, so this is the leftovers, right? So that's the one I'm going to have leftovers of. How could I figure out how much leftovers I have? What's that? Find out how much was used, absolutely. So if we want to find out how much was used, we'd need to find out how many grams of H2 were used. Same thing, same rule applies. Start all stoichiometric calculations with the limiting reagent, the thing that runs out, right? So what's the limiting reagent in this problem again? The nitrogen, so we're going to start with the nitrogen. Again, 1.7 grams of the nitrogen. And we want to figure out, what was that we were figuring out again? how much of this stuff was used. So what would be my final end stoichiometric goal in this case? Grams of H2. So I want to go from grams of N2 to grams of H2. So that looks like a 3-step problem, doesn't it? So we start with 1.7 grams of N2. Our stoichiometry flowchart. See, this is the hard part. The hard part was figuring out where you're starting and where you got to go to. So our stoichiometric flowchart, grams to grams, involves 1, 2, 3 steps. 1, 2, 3 conversion factors. Grams of N2 is going to go on the bottom, so it cancels. I'm going from grams of N2, using stoichiometry, to what?
Moles.
To moles of N2. Moles of N2 to moles of H2, because we've got to find out how much of it we used up in order to determine how much is left over, right? Now I'm going to take moles of H2 and I'm going to go to where? Grams of H2. Oof, this is a complex one. This is the hardest stuff you're going to do in this class, this kind of stuff. Moles to anything else, 1 goes in front of moles. We know this stuff how much it weighs, that stuff how much it weighs. Here's the hard part. Where does that information come from? Balanced equation, which is a page ago, which looks like N2 is a 1, right, and a 3. All right, so somebody with a calculator, tell me what that one comes out to be. And what are my units here? Grams of H2. All right, is that how much grams of H2 is left? That's how much we used. So how do we figure out how much is left? Right, so there's what we started with, 40.3 grams, right? So 40.3 grams of H2, and I'm going to label this at the start, so you can go back and double check, minus 0.364 grams was how much was used, which now gives us 39 and some change, I'll bet. 39 point what? 936. If we look at 2 sig figs, what should we do? I don't know. I'd say this, but that's only got 1 sig fig. There we go, right? Because that decimal does what to the 0? Makes him happy. Are we having fun yet? Let's do one that's a little more complex. Let's do something a little more complex, right? Just because you guys are having so much fun. You know, this is a lot like athletics, right? You had the quiz beforehand, so you get your mental muscles warmed up and you practice, right? And now now that you're warmed up, we're stretching you out and making you extend to the next phase. All right. Let's try, I want to do simple reagents so we don't have a lot of stuff to figure out the molar mass of. We'll use this one. I like this one. O2 as a gas plus H2 as a gas gives us good old H2O. You know, this is actually the reaction that could save our environment. This reaction could save our environment. If we could get cars to run on hydrogen gas, the oxygen that's in the atmosphere is already free. You're driving down the highway, you have a tank of hydrogen gas in your car. It's burning with the oxygen gas that's already in the atmosphere. All that comes out of your tailpipe is a little drip of water. No unburned hydrocarbons, no greenhouse gases, no particulates, no carbon monoxide, none of that stuff. All that comes out is water. The problem is creating enough hydrogen gas. Right now they do it through a process called coal gasification, which is an energy sink, which means it takes more energy to make the hydrogen than you get when it comes back out again. If we could figure out how to make photovoltaics, you know, the stuff on people's roofs, the solar panels, more efficient, we could use photovoltaics to do the splitting of water. This reaction goes in this direction. You can run electrical currents through water and it'll split it up into these things. We take photovoltaics on the roof of people's houses, split up the water, make hydrogen gas, fuel your hydrogen car. There's the answer to the future. So Detroit needs to work on that instead of more Hummers, in my humble opinion. All right, so if we start with this one, we say we got, oh my goodness, I'm going to start with 2.3 moles of this. And of this stuff, I'm going to start with 4.5 grams of that. And I want to know, actually, you know what? I want to know how much of this stuff first I need. Well, no, we can't do that because it's not limiting reagent. We've got to practice limiting reagent. All right, we'll start with, what did I say before the grams were? 4.5 grams of that stuff. All right, well, step one in our limiting reagent idea. And we know this is a limiting reagent problem, first of all, and this is a good way to just step back from the big picture and recognize it. First of all, you got a balanced equation, so you know that that's going to be the big kid stoichiometry, right, the two-substance stoichiometry. But then if you've got more than one substance as reactant where you have quantities that you have to work against each other and see which one is going to get used up first, then it is a limiting reagent problem. All right, so you can think about the stoichiometric calculations, doing it the easy way until you get to this point where it's limiting reagent. So step one, we've got to convert all quantities to moles, which we already have one of. So we have 2.3 moles of O2 gas we already have. So that's good, that's done. But now I got to take that 4.5 grams of H2, and I got to go from grams of H2 to what? Moles of H2. And H2 weighs 2.0 grams per mole, so that's going to give me 2.25 moles of H2. All right, so which one do I have less of? Oh, wait, nope, haven't done the next step. Try to jump ahead. Divide the moles by the coefficients in the balanced equation. That's why I always write this down, to keep myself straight. So I'm going to divide this number, 2.3 moles of O2, by what? By 1, because there is no coefficient, so we assume that it's 1, so we have 2.3 moles of O2. What number am I going to divide the moles of H2 by? 2. All right, so now I know I have 1.125 mole, well, that's not moles.
What would that be?
That's just a number, it's just a ratio.
Okay.
It's just a ratio that compares what you got to what will be used in this case. So which number is smaller? 2.302 or 1.125 of H2? 1.125 of H2. So then I'm going to mark this. Always mark this, and this will keep you straight. This is my limiting reagent, right? That is my limiting reagent. So then our steps in our stoichiometric calculation say, start all the calculations with limiting reagent, and there's our mole-bridge ratio. So now I've got, I could start here with my moles of H2, couldn't I? I don't have to start all the way back here with my grams, couldn't I?
You could.
So I could say 2.25 moles of H2. Where do I need to go from there?
You need to do the moles of.
I need to go from moles of H2 to, here I am, I want to go over to here. Let's see, what did the problem ask? No, we want to know how many grams of this. I didn't tell you that, that's the problem. How many grams of this stuff you want to make. So we want to go to moles of H2. So we're going from moles of H2 to moles of H2O, good. Remember, units and substance first before you put any numbers in. Moles of H2O down here. And what's going to go on the top? Grams. That's what I want to know, how many grams I want to make. All right. Coefficients for my mole-bridge ratio are going to come from,
The balanced equation.
so here's a 2 here
2 over
and a 2.
so 1 over.
So water weighs 18 grams per mole. So basically you could take 2.25, multiply it by 18. So sometimes you start at different places and you still have to get to the end result. What is our number here? 2.25 divided by 18. It's probably 0.
Divided by 18.
Oh, I'm sorry, multiplied by
It's
18.
40.5.
40.5, thank you. And that's grams of water. That's a couple of good drinks. Let's see, I know there's some homework problems. Let me check, since I've got 2 computers open here. Let me get a homework problem out. I'll do a homework problem for you.
Yes, please.
Yeah, oh, I know. No, Dr. White, please, don't do homework. Oh, percent yield. You know what? We haven't talked about percent yield. I just thought about that. Let's talk about percent yield real quick before we go on. I forgot about percent yield. All right, so in a perfect world, let's go back to this problem. This amount here is what's called the theoretical yield, right? The theoretical yield means that in a perfect world where I had a reaction vessel, that I could ensure that every molecule of O2 I had in that reaction vessel would collide at the exact speed and the exact orientation it needed with each H2 to produce the maximum amount of water, then that would be how much I could make in a perfect world. But as you might imagine, as a chemist, do we ever get 100%? No, it's just impossible. Chemists work their whole lives trying to improve. If you can get 80 to 90% yield, you're doing pretty good. So, if, for example, I did this experiment and I started out with my moles of O2 and my moles of H2 and I reacted them in a vessel and I didn't get exactly what I needed, say I got 35.7 gram is my actual yield, what do you suppose, if those are the numbers, percent yield formula is equal to? If I have a theoretical yield and an actual yield, what do you suppose my percent yield is going to be formula? There you go. See, you guys are so good with this stuff.
Which is
You're thinking like scientists already, and I've only had you for about 8 weeks. All right? You're thinking like scientists already. There you go. So what would I take? I'd take this number and divide it by what? 40.5 times 100, which would give me 88% yield, which is actually pretty darn good. If you get 88% yield out of a chemical reaction, you're doing pretty good.
it's
Sig figs. Yeah, you're right, 88.1. All right, well, we're going to stop there today. That's it. The homework I will post. Homework is due Wednesday, which is what we covered today. So the homework that what we covered today is not due to the day you take the exam. This stuff we just covered today is not due till the day we take the exam, and I'll post that homework. I think it's homework 13. Yep, let me put that up here. So homework 13 Make sure you add that. Homework 13 is due on Wednesday.
Hey, so, for the, I don't know if you told me to bring lab hard copy. I turned it into last Monday. Right after class.
What was it? What was the lab?
Maybe
Is it because you were missing the score in canvas? Okay, and so the paper you gave me shows the score that you had.
no, I don't. You never gave it back to me. I gave it to you last Monday. So I missed the October the 10th of lab.
Oh,
So I came in October 15th.
right.
So I turned it in, but I sent you pictures October 10th. I was finished with it.
Okay, but can you send me pictures October 10th? Okay,
I was done with
send
it.
me an email that says, send me pictures of my lab October 10th. Don't resend the message because Canvas does funny things when you resend something that has an attachment. But just send me an email that says, I sent you the lab, the lab on October 10th, then I'll go back and look at October 10th. Okay?
Thank you.
So just have a small question.
Sure.
The percent yield.
Sure.
Will we be given the actual yield and then we have to like calculate the actual? So it's always we're always going to be given.
Well, I will, no, you'll say, okay, yeah, you would calculate theoretically the product on the test. I would say, well, the actual yield was blah, blah, blah.
Yeah, and then you just use that to find. Okay. Thank you.
Sure. Hopefully the turn mic works.